So welcome to our second annual Science and Technology Summit. We're so glad the high school students are here with your teachers, and we have so many special guests. This is going to be a great morning, and our science faculty are really excited to get you over to do some science today. So thanks for being here, and we're real excited about the day. So first, a couple thanks. I want to give some special thanks to Jerisha Nixon and Dr. Edward Lewandowski of the NASA Glenn team for the gift bags and for coming to do the science activities. You all here today? Could you stand up if you're in the room? Those two folks? Yeah, very cool. Thank you. And also to Dr. Jason Kalirai from the Johns Hopkins Applied Physics Lab, because he's the one who made sure that you got that literature out there in the front as well. So, and wait till you hear him talk. It's going to be amazing. So let me frame up the day today. We have all of you here, about 200 of you, because we're celebrating you as part of the day. Those of you who are interested in science, we're looking forward to the future. Here in America, we want to generate a group of people coming up and our young folks who love science, who want to contribute to science, to help us as a nation stay strong in this area. We need you. Interested, tuned in, engaged. So today we're going to help that happen. We have about 12 different region schools that are here today, as far away as from Columbus, which is pretty neat. So this whole enterprise of science is amazing. My name is Dr. Mike Dunphy. I'm a biochemist. I'm also the vice president for academics here at the university. And I grew up loving science from the time I was about 12 years old. I thought chemistry was awesome, mostly because you could blow stuff up. But I learned later how valuable chemistry was as an area of science. Learned about biology, physics, geology, so many areas. How many folks in here like to be in a laboratory? Who likes that? A lot. Every hand went up. That's great. You're going to love it more as you get further along. If you're involved in science, you'll be in the laboratory. This event today is helping us to get you aware of the opportunities that are possible if you become involved in the sciences. When you finish high school and you go into college, you'll have choices. We hope you choose science as a path for you. We're looking for a way today to help excite you about the options and possibilities. We have folks here from NASA. We have folks here from the Applied Physics Labs at Johns Hopkins. We have folks here from Shimadzu Scientific, professionals who live this every day. We have faculty members at Walsh, same deal. These are scientists who live it every day. So we're going to have some fun. Looking forward to helping you see some opportunities. So I'm going to introduce right now Rebecca Coneglio, who's our Vice President for Enrollment, and she wants to say a few words about Walsh University, and I'll be right back.
Thank you, Dr. Dunphy. Again, I just want to welcome you all to Cav Nation. We're so excited to have you on our campus today. And I do want to just shout out the high schools that are here, because I think your commitment to the sciences and just showing up today on this wonderful, really cold November day, it just shows, again, your commitment to your students. So again, do a shout out to yourself if you want. So Central Catholic is here, Fairless, Glen Oak, Lake, Jackson, Louisville, Marlington, Massillon, and we have McKinley as well, Sandy Valley, and Tuslaw. So again, thank you all for your commitment. We're excited to have you. Today really is about the Walsh experience, so we take a very holistic approach to the student experience here at Walsh University. And part of that is the mind, body, and spirit and your growth in those areas. And the experience that you're gonna have today is very much what we do here at Walsh University. So this interactive, very hands-on experience that you're gonna have is very much what you would experience during your time here at Walsh. In addition to that, we make sure that learning transcends the classroom, and we do that in a number of different ways through experiential learning. So again, be sure to enjoy your experience, ask questions. We have a whole team here today to help you navigate the day, as well as if you continue to be interested in Walsh, how we can help make this your college choice. So again, ask questions, let us know if you need anything, and welcome to Walsh University.
Okay, great. So as Rebecca said, there's two focal points. One is to encourage you to find and develop and gain the knowledge and skills for a great career, and maybe many careers, but also to find your life's purpose, to figure out what that looks like for you individually. So the people we have here today have done that in different ways, and so we're interested in helping you see what they saw, what their journey was, and how they got where they are. So I'm going to introduce to you Dr. Neal Walsh, who's the chair of our Math and Sciences Division, who will introduce Dr. Stephen Leath.
Dr. Stephen Leath is past president of two of our nation's premier land-grant institutes, Iowa State University and Auburn University. While at Auburn achieved Carnegie R1 classification, placing the university among the country's elite research institutions. During his tenure at Iowa State University, the university achieved its highest student graduation rate, lowered student debt, grew research expenditures, set fundraising records, and secured the largest private gift for an academic facility and its largest cash gift. Prior to ISU, Leath served as vice president and research-sponsored programs for the 16 campuses of the University of North Carolina system. He has authored nearly 100 refereed journal articles, numerous book chapters, and other works. He holds a BS in plant sciences from Penn State University, an MS in plant sciences from the University of Delaware, and a PhD in plant pathology from the University of Illinois. In 2018, he was appointed to serve a 6-year term on the National Science Board. Please welcome Dr. Stephen Leath.
Thank you, Dr. Walsh. It's exciting for me to be here today. As you've heard, I spent most of my career in science. It's something I love and have a passion for. So when I sit here and see the next generation of scientists, engineers, it's pretty exciting because the world needs you folks and what you're going to do. So let me talk a little bit, but before I do that, I want to thank Walsh University. The people I've interacted with have been tremendous, and you folks are fortunate to be at this campus today because they have some exciting things going on. So for me, the STEM disciplines, science, technology, engineering, math, have been the heart of my career. When I was your age or younger, I loved science, I loved agriculture, I thought being in the lab was cool, I liked being outside. So I was fortunate that I could merge those things and became an agricultural research scientist, majored in plant genetics and plant pathology, and put those two disciplines together. So my expertise was going around the world, which was always fun, collecting wild ancestral species of crop plants, identifying important genes for things like drought resistance or disease resistance, moving into crop plants. I spent most of my career working on grasses, corn, wheat, oats, and barley, and felt I really made a difference. When you're feeding people and you're lowering food costs, and you're making people healthy who didn't have food before, you feel a great sense of accomplishment. As a matter of fact, one great American, Norman Borlaug, won the Nobel Peace Prize for this kind of work. And I say that because that's the kind of impact you folks could make in your careers and over your time. The STEM disciplines are hugely exciting, hugely needed, and that's not going to change except it's going to grow in relevancy and grow in importance. As you can see, working in these multidisciplinary fields like I did, helped me be a problem solver, led me to 2 university presidencies. It wasn't my planned career path, but it worked out really well, and I'm excited that I did it. And so now, the White House has put me on the National Science Board, where we write policy for the White House and Congress related to science, and we oversee the National Science Foundation, which provides a big part of the nation's science budget. But what we've really spent a lot of time on lately is a document called Vision 2030. Where does this country need to be in science and the other STEM disciplines in the next few years? And this is hugely important. We have big goals for the country, but what we're thinking about is critical to national security, it's critical to economic development, economic competitiveness, it's critical for health and well-being of our citizens. All of these areas need people. That's what's exciting for you, I think. At some point in your life, you're going to want a career and opportunities. The opportunities in these fields are endless and they're growing. It's a really exciting area to be, and you can mold these fields the way you really want right now because the demand for people with your skills and knowledge is huge and ever growing. So when you graduate, regardless of what level, undergraduate, graduate, the opportunities are there. They're going to continue to be there. Guys like me, I'm in the twilight of my career, but it's exciting to see what you folks are going to do next. There's a chance to create new knowledge, which is always exciting, apply new knowledge, take products, modify them, invent things to make them more relevant. There's also great opportunities to bring the derivatives of science to people who've never been able to use them before, to figure out how to assist people in using the great scientific discoveries in their everyday life. There's also a real need to develop ways to make science more attractive to a more diverse group of clientele. We need to be more inclusive and more diverse in science. All of you can help in that area. When we get a lot of people at the table or in the lab with different perspectives, different backgrounds, we tend to be more creative and more inventive. It's hugely important. So there's so many ways you can impact science right now. And if you think about this, every one of you probably sitting there with an Android or iPhone in your lap. You're working on social media. And if you think about the guys like Jobs and Zuckerberg, you might have wrote a report in Microsoft Word. You think about Bill Gates. These people changed the world, really. They changed the way we live. Now, that's probably more impactful for me because I grew up in a house with no color TV, no microwave, no cell phone, no internet. And it's probably hard for you to get perspective on that, but if you think about where I'm at or where your parents are, those kind of changes are out there for the next generation, and you're the ones that are going to get the chance to make them. You're going to think of things that people like me never thought of, never conceived of, or never thought possible in our lifetimes, but they're going to happen, and you've got the opportunity to make them happen, which to me is really exciting. If your passion isn't in pure science, if it's in communication, there's opportunities there too. Unfortunately, most of society doesn't really understand the STEM disciplines. We need communicators. We need science communicators like Maven the Raven, who's communicating science all the time. And I don't want this to sound like it's all about engineering and IT and those things. Think about what we just went through with COVID. It disrupted the entire world. But Kazmika Corbett is a virologist, immunologist. She pushed through that messenger RNA vaccine for COVID in 2 years. The whole world was watching, tremendous pressure on her and her NIH team, and she delivered. These are the kinds of opportunities and responsibilities that are out there. They're big deal things in jobs that are fun, exciting, and pay well. And best of all, and I think Dr. Walsh, others in this room could affirm, you get to meet some of the most interesting and creative people in the world, and you get to see the world. The science field is truly exciting and rewarding on a personal level as well. So from my perspective, I want you, I need you, I hope you get excited about these STEM disciplines and roll up your sleeves here. In closing, I'm thrilled to be with you here today. Anything I can do to encourage you or answer questions, I'll be around all day, I'll be glad to. But as I look out here, I see everybody's paying attention, so I think the future's in really good hands. Thanks, folks.
Awesome. Thanks, Dr. Leath. That was a good, great message. By the way, any teachers in the room, would you please stand up? The teachers that are here today, you're still here? And please stand, all the teachers present. Big round of applause for them. Woo! All right. Thank you for helping the students be here today, and thank you for helping them become excited about the sciences. So just for myself personally, I think the sciences are amazing. I think Dr. Lee's message about, inventing that which doesn't exist. How do we do that? We need bright young people like you engaging in invention, innovation, and things of that nature. And we tend to think of that mostly as here on Earth, the stuff we see every day, the stuff we use every day. Think about this. Imagine someone in 1950 portaling in here right now and seeing this thing. Could you imagine what they'd be thinking, right? Well, how about this? Thinking about space now, the other frontier. So how many of you have heard of astrophysics? Raise your hands. Astrophysics. Awesome. So the physics that's tied to astronomy, galaxies, comets, planets, all that wonderful stuff. Who's heard of NASA? All the hands are going up, right? NASA's been around a while. The National Aeronautics and Space Administration, they build rockets. They're involved in a lot of research. Who's heard of the Hubble telescope? Oh, yeah. What's the Hubble telescope do? Sends us what? What do we get from that Hubble telescope? Pictures, lots of cool pictures, right? And the Hubble telescope's amazing, and Dr. Kalirai will tell you about that. And how many of you know about the DART project, the most recent big deal, right? What was that? Anybody know? What did we do? Change the what? Trajectory of a asteroid. We did that from Earth. Amazing. Well, here's the really cool thing. The gentleman coming up here was involved in all of that directly. In fact, he led the team for the DART project. So today it's my absolute pleasure to introduce Dr. Jason Kalirai. He's internationally famous astrophysicist who works with NASA. He's involved in the Hubble and the DART project, and he's the mission area executive for civil space at the Johns Hopkins Applied Physics Laboratory. An amazing professional scientist, a powerful advocate for young people coming into the sciences, and an all-around terrific human being. I met him about half an hour ago. The guy's great. Dr. Kalirai, come up here, please, and give us your thing. Woo!
All right, I think I have a new hype man. That was great, thank you. Thank you all for being here today. This is a very special day for Walsh University and the community, and it really is my pleasure to share a few thoughts about science and technology and engineering with you today. I want to thank Walsh University. You guys are sitting at the nexus of business, of academia, of industry, making a lot of great things happen and really upscaling our workforce and getting ready for new innovations that we need to be successful. That's true in space exploration as well. Space exploration is going through a major boom right now. We've got hundreds and thousands of new organizations, new companies that have never been involved in space before but are getting involved in space. We have billions of dollars being poured into the space industry and new organizations creating new capabilities to explore space and expand humankind's presence in space. So it's an incredibly exciting time. There are lots and lots of opportunities and lots of connection points between science driven from academia, engineering, creating new technologies to solve critical challenges. One of our threads here today at Walsh is to enhance the quality of life through science and technology. And it's very intuitive to see that vision through the lens of things that we do right here on Earth every day. But what I want to do is take it up a level here today and talk about some of the boldest challenges that we face as a civilization, how we make those discoveries, and also what it tells us about ourselves, right? How it can reform our fundamental understanding of what our place in the universe is, how we got here, and the age-old question, are we alone? Okay, and I want to challenge all of you because I will say the universe has been kind to us. And we have the ability in your generation to answer that question, to answer the question, are we alone in the universe? The challenge is that the technologies to get there don't exist. You guys have to create them, okay? We will not be successful if we don't have you guys all in alignment, the best and brightest, coming in and helping support some of these pursuits. All right, let's get started. All right, so here's a picture of me and my daughter, and we're looking through a telescope, and we look at the night sky. I grew up in a small town in British Columbia, Canada, very similar to this. It was a small community, and one of the things that it afforded me was beautiful views of the night sky. We had very little light pollution, and so you could just stand in your backyard, you could look up at the night sky. And I had questions, what am I looking at here? Is this an appreciable part of the universe? Is this just my neighborhood, like the houses on my street compared to the city I'm in? How do I belong? How did I get here? How did we fit into the grand cosmos? And of course, you can go to your library and you can get a book and you can get an answer to that question. But the thing with space exploration is it's never satisfying. It just sucks you in deeper and deeper because the challenges that we want to address are even greater and it require a different dimension. My kids feel the same way. I think a lot of us get that inspiration from looking at space, and it drives our pursuits going forward. So I want you guys to do the same thing. When you guys look up at the night sky, challenge yourself, ask questions. Don't be satisfied by the answers to those questions. Go out and ask the next question. You know, NASA, most of you put your hands up when you were asked if you've heard of NASA. NASA's a household name. It's one of the biggest brands in the world, right? The agency's all about innovation, exploration, discovery, inspiration. I don't know how many of you have caught this morning, since it just happened a few hours ago, but Artemis 1 launched at 1 in the morning. This is NASA's next super rocket that's going to take astronauts back to the moon, and this time to stay, right? Not a one-way trip. We're going to go there, visit there for a week and come back, but we're actually going to build a sustained presence on the moon to extend humanity's footprints beyond Earth and use it as a stepping stone to get to Mars and to go even beyond that. Big milestone that happened 1 in the morning today. Our most powerful rocket that we ever have built took off. Okay, so one of NASA's crown jewels is the Hubble Space Telescope, and most of you put your hands up when you heard about Hubble as well. Hubble is an incredible technological asset. This is a telescope that cost us billions of dollars, and it basically opened our eyes to the universe. It made the universe much more colorful, much more accessible to the whole world. You can walk the halls of Congress and you'll see Hubble Space Telescope pictures hanging from the wall. It's inspirational. Hubble has made countless discoveries. I just want to show you one, and it's the only picture I'm going to show you from the Hubble Space Telescope. So this is a video, and it's a video that shows a tiny, unobscured patch of sky, and we opened the shutters of the Hubble Space Telescope, and we just started collecting light from the universe. And where all other telescopes see nothing because there's emptiness, with the power and the sensitivity and the clarity of the Hubble Space Telescope, we saw a universe teeming with galaxies, different shapes, different morphologies, different colors. There are more than 10,000 galaxies in this single tiny little patch of sky, which is equivalent to looking up at the night sky through a drinking straw. In that tiny little patch of the night sky, there are thousands and thousands of galaxies. So if you ask yourself, how many of those tiny little patches of sky would be required to cover the entire night sky? And if there are 10,000 galaxies in this image, what does that mean in terms of how many galaxies there are in the universe? And every speck of light you see here, even the small little specks of light, are galaxies with millions and billions of stars. The answer is that there are 100 billion galaxies in the universe with 100 billion stars each. Some of them might have millions, some of them have trillions, right? So the number of stars in the universe is a 1 with 22 zeros after it. Punchline is we are not special, okay? The combination of science and engineering has taught us that over and over again, right? Galileo, a scientist, took a piece of engineering, a piece of technology, pointed it up, looked at Jupiter, saw some things that he thought were background stars behind Jupiter, but then quickly discovered those are actually moons of Jupiter that are going around Jupiter. So if there are other objects in our solar system that are not going around the Earth, it means that we are not the center of the universe, right? We are not special. Edwin Hubble, who the Hubble Space Telescope is named after, looked up at the night sky and saw some fuzzy patches, and he realized those fuzzy patches were not in the Milky Way galaxy. They were entire galaxies out there, he called them island universes back in the day. Again, we are not special. This is the latest data point on that. Now, the story gets better. If you look at nearby stars in our Milky Way galaxy, and you look at them edge on, right? So if they're in a pancake configuration instead of a face-on configuration, and you take pictures of those stars over and over again, what you will see is you'll see periodic dips in the starlight. No difference than a solar eclipse where the moon comes in front of the sun and it gets dark outside. Same thing. These are planets that are orbiting nearby stars. So we built a telescope called the Kepler Space Telescope to do an experiment and take pictures of a small part of the Milky Way galaxy over and over again. Just take pictures over and over again. And what Kepler found is that there are planets orbiting all of these stars, okay? So again, the universe has been kind to us, and here's a picture of the distribution of planets around other star-planet systems. Some of these are the very stars that you can see with the naked eye when you look up from your backyard. And there are thousands of them within this tiny little field. So if you ask yourself, given the systematic biases and the inefficiencies in the experiment that we're conducting, what does that mean for how prevalent planets are around stars? And the answer is that planets around all the stars, okay? So you've got all of these stars in the universe, and guess what? They all have planets, okay? This is remarkable. This is a discovery from less than 20 years ago. When I was a kid, there were 9 planets that we knew, right? 9 planets in our solar system. It went to 8 when we kicked Pluto out of the solar system, right? And now we know that there are more planets in the universe than stars, because when a star forms, a star can form multiple planets. So don't quote this, right? But when a star forms, there's gas and dust, right? The gas and dust, it coalesces in the center, and the temperature can get hot enough and the pressure can get high enough that nuclear fusion starts and a star is born. But some of the gas and dust is just laying around, and it coalesces and it makes rocks. So planets are a natural outcome of the star formation process. It's just the debris laying around after a star forms. That's what the Earth is. It's just a rock with a bunch of debris related to the sun and when it formed. So anywhere you form a star, you form planets. And furthermore, Kepler actually tells us that most of the planets that are out there are not the Jupiter, Saturn gas giants. Those are rare. Most of the planets are small, rocky bodies, right? In fact, everything in the universe is tilted towards a size distribution of smaller objects being more prevalent. Okay, so this is your challenge. This is your generation's challenge. You've got all of these worlds out there, and yet there's one world that we know life exists on, right? So let's go out, let's go explore these planets, conduct new experiments to detect biosignatures, and see if there's atmospheres in these worlds that have compositions that would not exist if life wasn't prevalent on those worlds. I'll give you an example of that a little bit later. Now that said, let's back up for a minute. We've got our beautiful blue marble here, right? Planet Earth, and this planet is teeming with life, and we have to take some steps to protect that life as well. So let's make sure we're thinking of our own planet. There's many ways to do that on the planet, but we're involved at APL in looking at how we bring together different organizations to address the challenge of protecting our planet Earth from space hazards. The DART mission that we alluded to is a great example of that. So I want to talk about 2 space hazards today very briefly. One is planetary defense, that's protecting our planet from asteroids, right? We know this can be serious. The dinosaurs were wiped out by asteroids. Our planet is getting hit by an asteroid that's about 1 meter across every 2 weeks, okay? Once a year, we get hit by an asteroid that's bigger than the table you guys are sitting in. And once every 10 or 20 years, we get hit by an asteroid that's much, much larger than that. You look at that blue marble, you think of Earth kind of being by itself, isolated in space. That's not the reality. There are thousands and thousands of these asteroids in our solar system. Many of them are in that band called the asteroid belt between Mars and Jupiter, but a lot of them are also in the inner solar system, and they have trajectories that overlap Earth's trajectory. So here's an example of one. This is a dash cam footage of an asteroid that about 10 years ago that flew over a city with more than 1 million people, and this asteroid burst and exploded over the city. The shock wave from that explosion was 20 times greater than the atomic bomb that was released during World War II. This caused widespread damage. People got injured. You can see some video here. Here's a gentleman that just avoided a piece of the roof collapsing right in front of him. He was headed right for that location. Here's a woman talking to a colleague in an office, and you can see her colleague is going to get hurled through a door when that shock wave hit that building. And here's a really scary one. The next one, you can see some school kids, and they're listening to their teacher, and that explosion happened. They're holding their ears. They're very worried about what can happen. So this is dangerous. The probability of this happening is low, but the consequence of happening is very high, right? And the potential damage could be catastrophic. So NASA has stood up a planetary defense office. There's a planetary defense coordination office. They have funding from the US government to address these challenges. And there are 3 goals from this program. One is, let's go find all of the asteroids that could be a threat to Earth, right? We want to determine what the census is. Number two, let's go characterize them, right? Let's figure out what their sizes are, what their compositions are, what their trajectories are. So if they were to hit Earth, we could predict what the damage is going to be. And number three, let's do something about it, right? Unlike the dinosaurs, if there is an asteroid coming towards Earth, let's create the technologies that we need to help ourselves and protect ourselves from such a threat. That's where the DART mission comes. So DART is the Double Asteroid Redirection Test. It was a mission that was inspired and created by scientists at the Johns Hopkins Applied Physics Lab. And then it was designed and built with APL leadership, but partnering with a whole slew of new industry, including new space companies that are just getting online. The goal of DART is to hit an asteroid and move it in space. The target asteroid system is very important. You need something that's close by. You need something that you can observe from Earth. And you need something where you can measure the impact of the collision. If you just have an asteroid in space and you bump that asteroid a little bit, it's very difficult to measure if you actually change this orbit because it's going around the sun. In the case of DART, one of our scientists, Andy Chang, came up with this very creative idea of targeting a binary asteroid system where we've got a large asteroid that's about 1 kilometer across and a small asteroid that's about 160 meters across, and the small asteroid takes 12 hours to go around the large asteroid, and we can measure that rotation using ground-based telescopes from Earth, many of which are funded by the National Science Foundation. And if we bump that small asteroid, we can change its orbit around the big asteroid and then just remeasure what its new orbit is. So it's a well-designed experiment. We launched the DART mission almost exactly a year ago, Thanksgiving Day, right before Thanksgiving Day last year, 2021. I watched this launch from just about a mile back from where this picture is taken. Whole family was there. It was incredible. It marked the culmination of 5 years of hundreds of scientists and engineers coming together and doing something incredible. Picture perfect launch on a SpaceX Falcon 9 rocket from Vandenberg Space Force Base. And here's, I'll pause this for a second. Here's the design of the experiment, okay? Oops. So what you're gonna see here is Earth in the inner circle. The Earth takes 1 year to go around the sun, as you guys know. And then that outer circle is the asteroid system. So that's both asteroids, the primary and the binary. In reality, the small one's going around the big one, but you're just gonna see it as one dot. And that asteroid system, which we call Didymos and Dimorphos, takes 2 years to go around the sun. But the path of Earth and Didymos and Dimorphos gets very close at a certain point. So I'm gonna run this movie. There we go. Okay, so here comes Earth. There's Didymos. When the Earth gets at about like 2 o'clock there, you're gonna see DART launched on November 23rd. And then DART is now that little yellow dot that's trailing Earth, right next to Earth. So DART, through the last year, has stayed very close to Earth. And then it goes past Earth and it's closer to the target than Earth, and that's where we hit the target, okay? So the distance between Earth and the target got closer and closer. DART stayed close to Earth over the last year, and then we hit the target. DART is only possible because a wide range of industry came together to address some of the technical challenges that we had in making this experiment successful. So for example, the power of DART comes from rollout solar arrays. This is a brand new technology, never been flown in space. We've literally taken a piece of fabric and put solar cells on that fabric so you can roll it up and then deploy it in space. Small form factor, lighter weight, enables us to do different kinds of exploration in space in ways that we couldn't before instead of having giant rigid solar panels. That's a technology that was created by a company with 80 people called Deployable Space Systems in California, a new startup space company. You look at the Nexi ion propulsion engine, that's a engine that uses xenon and accelerates xenon ions to provide an extra thrust and an extra boost for the spacecraft. And then you look at, it's not just hardware, right? If you look at autonomous smart navigation system, that's the guidance system that the DART spacecraft used to autonomously guide the spacecraft into its target. There wasn't a human in the loop. We didn't have somebody in our mission control center with a joystick taking it into its target. It was all autonomously done on the spacecraft. Lots of other great technologies too, including collaboration with international organizations. So the Licia CubeSat was provided by the Italian Space Agency. We deployed it 15 days before our impact, and it trailed us and took pictures of the impact. The result of this experiment was very successful. I think everybody has probably seen these pictures. These are some of the last few pictures of our target asteroid. Remember, this asteroid was never seen before. It's so small and it's so close to its bright neighbor that we'd never seen it before. So we saw it for the first time when we were about an hour from impact. We live streamed this to the whole world. And then you can see boulders on it just a couple minutes before impact. That's our final image right before impact. And then our last image was our loss of signal. Everybody was crying. It was amazing. This was very nerve-wracking, but it was incredibly successful. So we hit the asteroid bullseye. We hit within 2 meters of our target, flying 14,000 miles an hour into an object that's only 160 meters across. Here's a picture from the Hubble Space Telescope of what we did. We just obliterated this thing, okay? We hit this asteroid. Our requirement was to move the asteroid in its orbit around its primary by 73 seconds. We thought if we have a perfect experiment, we would be able to move it by 10 minutes. We moved it by 32 minutes. And the reason for that is we hit it so hard that the ejecta from the asteroid shot off, and that ejecta induced an additional kinetic impact on the asteroid and moved it even further. So anyways, very, very successful experiment. This is just one technology for planetary defense. This is just a brute force, build a spacecraft, 600 kilogram spacecraft, fly it really fast and hit an asteroid. There's all sorts of other more novel ways that you might be able to, you detect an asteroid early enough, you bump it a little bit, or you put a little thruster on it to deflect it, or you use some kind of a laser, you ablate it. You can do all sorts of things to slow it down a little bit so the Earth gets out of the way, the asteroid flies by, and we're safe. And so over the next 10 years, 20 years, NASA's going to be investing in these kinds of technologies, partnering with industry, partnering with academia for new answers, partnering with government labs and other independent labs, not-for-profits, to address future goals in planetary defense. All right, the second space hazard I want to talk about just briefly is related to our sun. Okay, so it's easy to look at a picture of the night sky and lose the perspective that every single one of these dots that you see, these specks of light that you see, is a giant ball of hydrogen gas. Okay, our sun is 99.8% of the mass of our solar system. You could stick 1 million Earths into the volume of the sun. Energy generation on our sun is equivalent to billions of hydrogen bombs going off every second for billions of years, okay? Our planet, Earth, and every other planet out there is at the mercy of what its star decides to do. And so there's a word called space weather. Space weather refers to the flow of radiation and particles from the sun. Normally it's flowing in all sorts of different directions, but occasionally you can get a coronal mass ejection, you can get a solar flare that channels that radiation, millions of tons of plasma towards a specific direction. Fortunately, our planet, Earth, has a magnetic field, and the magnetic field of our planet protects Earth from this harmful radiation and prevents it from hitting our world. It does interact with our world. Anybody that's seen the aurora borealis has seen the interaction of energetic particles with the upper atmosphere, energetic particles from the sun with the upper atmosphere of Earth. But if we have a giant coronal mass ejection like the Carrington event, you guys can look it up from the 1850s, it could be very disruptive, especially in a modern technologically advanced society where we have, it could take out our power grids, take out our telecommunication systems, aviation, and our national security and space-based assets as well. In fact, this year, SpaceX failed to get 50 spacecraft up into their orbit because of a space weather event that resulted in a thermospheric expansion in the atmospheric layer, and those spacecraft didn't have enough propulsion to get beyond that. So space weather impacted that launch directly. So we want to understand what space weather is, and similar to planetary defense, we want to increase our warning time and try and mitigate the impacts by safing our spacecraft, turning off our power grids, etc., before they get damaged. So we're very involved in this at APL in many different ways. One way is the development of new missions, missions that are literally flying to these sources, flying to the sun, flying through the atmosphere of the sun. This is a marvel of engineering. It's a mission called Parker Solar Probe. It's about a $1.5 billion mission that we led the design for at APL, partnering with hundreds of organizations across the country, inspired by scientists more than a half century ago, but the technologies were lacking to make it happen. Normally, we're studying the sun from a distance of 93 million miles. That's the distance between the Earth and the sun. With Parker Solar Probe, we've now flown within 5.5 million miles of the sun. And we're also going to approach 3.8 million miles in the coming years. It's not just about the engineering and hardware. One of the things that makes Parker Solar Probe so successful is the analysis that happens, the computational simulations. And so one of our engineers, by the way, here's a picture of the thermal shield. This is what protects the spacecraft when it's going very close to the sun. It's a carbon composite material. It's about 4 inches thick, 8 feet wide. This thermal shield can reach temperatures of 2,500 degrees, and it protects the spacecraft and the electronics and the instruments that are behind it, which are at room temperature. And it's been working really, really great. But one of our engineers came up with a mission design that's enabling for Parker Solar Probe. So the reason that we're able to do this science is that when we launched the spacecraft, we flew past Venus, and we gave a little bit of momentum from the spacecraft to Venus, and then it came in and it did a closer flyby of the sun. So this is the orbit of Parker Solar Probe. It did a little flyby of Venus, and it comes in a little bit closer. And then it stays on that orbit for about a year, and it'll do 2 or 3 more passes of the sun. And then the next time we get a chance, we do another little flyby of Venus. We give a little bit of momentum to Venus, and we drop the spacecraft in a little bit closer to the sun. So repeatedly, we're able to take advantage of a natural body in our solar system to slingshot the spacecraft and get closer and closer to the sun. There are more than 700 research papers that have been published from Parker Solar Probe, unique science highlights because of the vantage point that we're at. This is sorry, oops, I hit that too many times. Here, I'll show you guys this one. So this is another mission that's studying the sun. It's called Solar Orbiter. And this is a video of the, it's not playing, it's too bad. Okay, anyways, this is a picture of the south pole of the sun. This is the kind of clarity and resolution that we're able to get with different missions that are working in concert with Parker Solar Probe. This is a European Space Agency mission, also very, very impactful, telling us a lot about how our star generates energy, how our star influences our solar system, and the source of some of the space weather phenomenon that we're trying to mitigate. Okay, back to life. So that's a little bit about protecting life. I talked about how the universe has been kind to us because it's, stars are everywhere, and all of these stars have planets, and so we can go out and explore them. But there's also a different kind of exploration that we can do right here in our backyard. When you look at a picture of Earth, one of its most distinctive characteristics is its ocean. And for a long time, we thought that the Earth was unique with respect to the solar system and with respect to other objects, because it had water on it, and water is one of the necessary ingredients to life. It turns out that's not true. Recent exploration within our own solar system has revealed that oceans are actually abundant in our solar system. One of the key differences is that these oceans are subsurface oceans and not surface oceans. So for example, many of the moons in our solar system, the moons of Jupiter and Saturn and Uranus and Neptune, have ocean worlds, and many of those oceans have more water than we have here on Earth. Here's a little video. This is from a documentary from James Cameron, I think. It's called Aliens of the Deep, and it shows, this is an animation of what it looks like if you were to dive in and go to the bottom of the ocean floor and what you would see in the bottom of the ocean floor. And as you go through this video and you go deeper and deeper down, the video is going to transition from an animation to actual footage that we've collected on the bottom of the ocean floor. And what you see is that in these conditions at the bottom of the ocean, where there's intense pressure, there's no sunlight, we have energy sources. We have hydrothermal vents pumping heat into the ocean, and we have life, right? We have life thriving in these intense, extreme regions of our ocean. So if life can be thriving in our ocean in these extreme conditions, what's to say it doesn't exist already right in our backyard around some of the ocean worlds and the moons in our solar system? So we have a program at NASA, an astrobiology program, which is studying these ocean worlds using new innovation, using new technology. These are some of the biggest missions that are being developed in our country right now for space exploration. It includes a mission to explore habitability on Europa, which is the nearest ocean world. That's a moon of Jupiter. It includes a mission to visit Titan, which is a large moon of Saturn, where there's liquid methane, there's methane rain, there are clouds, there are lakes and seas. And it includes a concept mission that we hope will be approved soon to land on one of these ocean worlds and actually taste the water that's on the surface. Let me just say a few words about each one. Europa Clipper, this is a $5 billion mission that includes hundreds and hundreds of contractors working together with the U.S. government to build this mission to go to Europa. Europa is an exotic destination. It's got many of the conditions necessary for life. It has a saltwater ocean with 2 times the volume of water than Earth. It has chemistry because this ocean is in contact with its rocky mantle. And it has energy, both gravitational energy because it's orbiting Jupiter, as well as energy from sunlight. And so we're going to go and do a comprehensive experiment on Europa to explore habitability on this surface. This is a mission that's launching in less than 2 years. Titan is Saturn's largest moon. It's one of the most exotic and Earth-like worlds out there in our solar system. It has an atmosphere that's thicker than Earth's atmosphere. It also has less surface gravity. So if you have a lot of air and very little surface gravity, it's a perfect place to fly, right? And it has all of the conditions, ingredients necessary for life. Energy from sunlight, liquid water, also has complex organics. This is a chart that shows the amount of carbon in a number of bodies in our solar system on the right-hand axis. So for example, Saturn has a lot of carbon, but the carbon isn't doing anything. On the left-hand side, the little arc that you show is the most complex carbon-bearing molecule. Titan is the only world that looks similar to Earth here in terms of the complexity of the molecules. So we proposed a mission called Dragonfly, and NASA selected it. This is a mission that we're building at APL right now together with many different partnerships across academia and industry. And it's a mission that's going to land a nuclear-powered dual quadcopter on Titan. This is something that's about the size of your car, okay? So it's about the size of the rovers on Mars, except it's going to fly instead of roving. So here's an animation. So as soon as we get out of our aeroshell on our descent, we're going to spin up our rotors and we're going to fly. And then the spacecraft is going to, the lander, it's not even a spacecraft at this point, it's going to autonomously find a safe place to land on the surface. And once it lands there, it's got a drill. It can drill into the Titan soil and taste that soil. It can, it's got seismometers, it's got a weather station. It has a gamma ray neutron spectrometer to do compositional analysis. There's cameras everywhere. And then once we're done doing science at a certain destination, we're going to fly tens of kilometers, find another exciting place to study Titan, land, and do science there. So very exciting mission. We're launching this in 2027. You'll be hearing a lot more about it. I think you have a flyer on your tables with some more information on it. And then this is an ocean world orbiting Saturn also, small moon, where the Cassini mission saw water venting from the south polar axis of this mission. And so we want to build a mission to actually land on the surface. It's called Enceladus Orbilander. Technologies for this mission don't exist right now. This is a great opportunity. But we can first orbit the moon and sample some of the smaller particles that are coming out from this ocean and do astrobiology. We can also land on the surface and capture with a scoop that you can see in that picture right there, some of the larger particles. And then we're basically building some of the sample collection mechanisms and looking for how we would distinguish on board, right? Not bring the sample back, but on board, whether or not there are biosignatures, whether or not there's life in these oceans. And we can detect life with the technologies that we hope to mature that's 500,000 times more scarce than Earth's oceans. So incredibly inspirational, incredibly exciting kind of discovery within our solar system to move the pursuit, search for life forward and understand better what our place in the universe is. I want to end with the James Webb Space Telescope today. This is one of the largest projects that NASA has ever undertaken. This is a $10 billion mission. At its peak, there was more than 1,000 scientists and engineers working on this mission every year. Over its lifetime, there have been tens of thousands of scientists and engineers that have worked on this mission. This is our new golden eye in space. And many of the technologies that enable this mission to be successful didn't exist at the time that the mission was being formulated. Many of them have tremendous spin-offs that help humanity as well. So for example, the quality of the optics that you need on this telescope exceeds anything that we had in labs to diagnose ocular diseases. And so when next time you go to an ophthalmologist and you get your eyes checked, some of the technologies that are in those devices came from spin-offs from the James Webb Space Telescope. So there's lots of examples like that I can go into. Let me show you a couple pictures from James Webb to close this out. This is a picture that looks like something's wrong, right? It looks like something's out of focus. You see all these little arcs and loops and things like that. This is Einstein's general relativity at work, okay? So what you're seeing here, you should think of space as being a fabric, right? So imagine where you and I are holding a blanket and we stretch it out and then we drop a marble on that blanket. That marble is going to create a divot in that blanket. That's what happens to space. Where there's a big piece of mass, a star, a galaxy, that star or galaxy will bend space itself. So what's happening here is there's a cluster of hundreds of galaxies in a tiny region of space that's completely warped that region of space. And the light from background galaxies that has nothing to do with that cluster has to pass through this region of space that's warped. And so all of those arcs that you see there are the same background galaxy lensed multiple times. It's like taking a wine glass and putting it on a table and there's a light bulb above that wine glass. You'll see the light warp around the wine glass. It's the same thing here. We can use this to understand general relativity and test general relativity. We can use this to understand the dark matter distribution. And we can actually use it to see further into the universe because of this lensing effect. It amplifies the light, basically. Here's a beautiful image of actually 5 galaxies, but the 4 galaxies that you see on the right-hand side are galaxies that are physically interacting with one another. These are galaxies that are accreting one another and growing over time. The galaxy that you see on the left has nothing to do with those 4 galaxies. It just happens to be along the sight line and is in front of those galaxies. So a nice example of the cosmic dance that major galaxies do, just like our solar system is changing and moving, just like our planet, life on Earth is changing and over time and evolving. The same thing is happening on the grandest scales out there. And it's the optics and the detectors and the instruments on James Webb that took years and years of development that enable images like this. Okay, so this is one where, I showed this to Dan the other day, and he said, wait, is this real? Like, it looks like, something like one, those spray paint artists on the side might have created this beautiful, science fiction visual of the night sky. This is a real image from the James Webb Space Telescope. In fact, this is pretty close to us. This is like a couple thousand light years away. It's right here in our own galaxy. And it's a stellar nursery. This is a life cycle of stars. You have lots of massive stars that are turning on. They're burning, they're evolving, they're dying, they're impacting their surroundings, they're expelling their gas into their surroundings and seeding the next generation of stars. And then there's this beautiful barrier here because the gas from all of that star formation, the expansion has only reached a certain point, and there's ionization from the neighboring stars. So just a really, really outstanding image. It's like a painting, right? I mean, I've sat and looked at this thing for an hour. It's just beautiful. And then finally, back to life, right? Here's a spectrum of an exoplanet. This is a planet orbiting another star in our galaxy. And the James Webb Space Telescope looked at the light from the star as the starlight goes through the planet's atmosphere and measured the planet spectrum. You're detecting water vapor in another planet. This is an easy experiment for James Webb. Over the coming years, as you guys get into undergrad and start doing research, you'll be hopefully designing some of the first experiments with the James Webb where we'll be looking at rocky planets and we'll be searching for oxygen, we'll be searching for carbon dioxide, we'll be searching for biosignatures in the atmospheres of these worlds. Okay, so I'm gonna end with that and just say that, space exploration is an incredibly exciting field. It's one of many exciting fields right now. It's something that's not possible without, people from different backgrounds working together to address tough challenges and, always kind of pushing beyond, right? You can reach and see something. You can see that deep field from the Hubble Space Telescope. The reason we have the James Webb Space Telescope is that as impressive as that deep field was, there were people that said, that's not enough. What's beyond that, right? How do I reach even farther? That's the inspiration that led to the James Webb Space Telescope. And no matter what you decide to do, hopefully it's in science, technology, engineering, or math. I'm biased. Always try and push beyond what you think is possible. And that's where that real inspiration and that real push for technology comes from. Walsh University is at the nexus of that. I mean, the way that Walsh University interacts with local communities, with industry, with other academic organizations, upscaling our education for not just students and bringing them in through internship programs like we have today, but also partnering with local industries like Mack Trailers, for example, and helping bring new innovations through digital engineering and computational efforts that increase their efficiencies and train their workforce to be more successful. That's happening around the world. It's a really, really exciting time. So thank you all. I will try and stick around here. If anybody has questions or wants to chat about anything, feel free to come up. And again, I'm very honored to be here today, and I really enjoyed talking to you guys.